This is Math 251, sections 11.1 and 11.2, part A. We're going to be looking at an introduction to vectors in 2 and 3 dimensions. And we'll begin by talking about vectors, what they are, and what it means to put them in standard position. First of all, up until now in math, mostly we've used values that are scalars. A scalar is simply a number. It designates quantity or size. For example, if I say that a particle is moving at the rate of 4 meters per second, that speed, 4 meters per second, is a scalar. Essentially, it's the quantity of meters that we move in a second. What this doesn't tell me is which way I'm going. If I want to do that, I need a vector. So a vector is a mathematical object that designates both size and direction. For example, suppose we have a particle that's moving 4 meters per second in the direction due north. Which of the pictures on this page show that? Well, let's see. Looking at this first picture, I can see that using sort of the standard way maps are drawn, up is due north. And so the fact that 1, 2, 3, 4 is the length of this vector seems to indicate that I am going 4 meters per second in the direction due north. What about this one? Well, it shows the same thing, doesn't it? The vector is still 4 units long, so that's its size, indicating a velocity of 4 meters per second, and it's pointing due north. In general, we're going to go ahead and say that we'll always consider when we're drawing, we'll always consider the x-axis to be east, the y-axis to be north, which would leave south going down and west going to the left. And that's typical, right, when we make maps. So we'll continue to do that here as well. So far, both of these vectors seem to be indicating 4 meters per second due north. What about these? If I stick with the idea that the positive y-axis is north, this would be north, meaning that's south. Positive x-axis is east, and the negative x-axis would be west. Z is typically up and down when we go into 3 dimensions. But what you're seeing here is this vector pointing the same direction as due north again. And if you kind of take a look, it is 1, 2, 3, 4 units long. So 4 meters per second due north could be represented by this picture as well. This last diagram actually puts all 3 of the vectors on the same plot. I just used Maple to do this, and eventually we'll talk about how to graph vectors in Maple. But notice this is just the 2 vectors, the green and the blue ones, that were in the xy plane. They were the ones you saw up here. And then this red one goes in the direction due north. This would be the y-axis. This would be the positive x-axis. And up would be the positive z-axis in just the orientation that I rotated my Maple picture to show you. So, all pictures. Show 4 meters per second. Running out of ink here. 4 meters per second. Due north. What this does is illustrate a concept in vectors called freedom. Vectors are free, meaning they may look different. They may start in different places, and yet they really represent the same vector. I'm going to go back to the 2-dimensional picture for just a moment. These 2 vectors had different starting points. We call that their initial point, by the way. But they both went exactly for a distance of 4 units, and they both went straight up. So they actually represent the same vector, just with different starting points. We talk more about this idea of the freedom of vectors on the next page. So again, there's that definition right at the top. Vectors are free, meaning that if we can move them left, right, up, or down, but they'll still be the same vector. because it still designates the same size and the same direction. So always have the same vector if same size and same direction are satisfied. This does mean that I might have two vectors that look different because they start in different places, but are really the same. This idea in math that two things can look different but be the same, you've seen it many, many times, right? 1/2 and 3/6. They look different, but they're the same number. The square root of 8 and 2 square root 2 look different, but they're the same number. This is just the equivalent of that idea, but for vectors. So two vectors might look different because they start in different places, but really represent the same vector. Usually when we have multiple representations for something, we have kind of a simplest or preferred form, like lowest terms for a fraction, or simplest radical form for a square root. With vectors, our simplest form is to put the vector in what we call standard position. A vector is in standard position if its initial point is at the origin. So in the problems that we were working with, our vectors were supposed to be 4 meters per second, so 4 units long, and go due north. I could draw that by just starting my vector in standard position at the origin, and then drawing a vector of length 4 straight up, or due north. So that's the same vector as the ones on the previous page, but now it's in standard position. I could do the same thing in 3 dimensions. Standard position means we always start from the origin. North is the y-axis. So I just want to go 4 units along that y-axis, or due north. Now that we have our vectors in standard position, we're ready to talk about notation for them. To give notation for a vector in standard position, we don't have to explain what the starting point or initial point is, because the initial point, starting point, is always the origin. So I don't have to tell you that. If it's standard position, you already know it. All we have to do is specify the terminal point. The terminal point is where the vector ends. In order to say that we're giving you a vector in standard position, we'll specify the terminal point and we'll use angle brackets around it. And that's how you'll know, hey, I'm being given a vector in standard position. So, in this case, the terminal point is the point 0, 4. And if I'm only referring to the point, of course I use parentheses. But if I want you to know I'm referring to that standard position vector, I would write it using angle brackets. 0, 4. I'm now referring to that mathematical object that is the vector, starting at 0, 0 and ending at 0, 4. I could do the same thing with the 3-dimensional one. In 3 dimensions, the terminal point for this vector would be 0, 4, 0. And therefore, the 3-dimensional vector in standard position could be written as 0, 4, 0 with the angle brackets. A little bit more vocabulary. Each entry in the vector notation is called a component. So if you look at this 3-dimensional one, the x component is that 0, the y component is the 4, and the z component is this last 0. All right, so let's talk about how to take a general vector, one that's not initially given to us in standard position, and rewrite it as a standard position vector. Little note at the top of this page, from here on I'm always going to give definitions and theorems in terms of 3 dimensions. If you happen to be working in 2, of course you can just ignore the 3rd component. So here we go. Let's suppose our vector v is a vector that goes from the initial point P to the terminal point Q. In standard position, of course the initial point is 0, 0, 0. That's what standard position means. And to find the terminal point, ABC, we just subtract x2 minus x1, y2 minus y1, and z2 minus z1. Our vector in standard position can then be written with the angle brackets, ABC. In order to remember this, trying to memorize this as a formula or have to look it up every time is counterproductive. Most people just remember it with a little sort of phrase. To find its standard position, just think terminal point minus initial point. So we've literally taken each coordinate for the terminal point and subtracted its coordinate in the initial point. A couple other quick little things here about notation. Here's a couple of different vector notations. I can give a vector a name and just call it v. Or if I want to tell you what its initial and terminal point were, I can call it the vector from P to Q, or the vector PQ. Both perfectly acceptable notations. One other quick note about notation. I'm putting these little arrows over my vectors to indicate that they are vectors. I do that mainly because when I teach face-to-face in a classroom, I can't use bold type when I'm writing by hand. In your book, rather than the arrows, they're going to use bold type to indicate a vector. It's hard to do that when you're just jotting things down by hand or working problems on paper. So I like the little arrows over them just to remind me that they are indeed vectors, even though I can't write in bold. All right, so a couple of examples for finding standard notation, or sort of standard position rather. We're going to draw each vector the way it's described, and then we'll calculate the components in standard position and redraw. So V is the vector from 5, 2 to 2, 2. So there is the original vector. From 5, 2 is our initial point, 2, 2 is our terminal point. To calculate the standard position, I take terminal minus initial. So terminal minus initial. 2 minus 5 would be negative 3. 2 minus 2 would be 0. If I now draw this as a standard position vector, standard position means I start from the origin, and my ending point is supposed to be negative 3, 0. And so there's the same vector in standard position. I'm sure you can see visually that it's the same, it's just been slid over and down. But we can also see mathematically by taking the terminal point minus the initial point, we can get our standard position notation. Let's do that one more time. This time W is the vector from 1, negative 4, it's my initial point, to 3, negative 2. There's my terminal point. To calculate the standard position vector W, again I'm going to take terminal minus initial. So 3 minus 1 is 2. Negative 2 minus a negative 4 would be a positive 2. And that standard position vector always starts at 0, 0, and it ends at 2, 2. So there we go. Same vector. Again, you can see it's just been slid left and up. There it is in standard position. All right, that was a two-dimensional example, so it was pretty easy to graph. Let's finish up this part of the video by just doing a couple quick examples in 3 dimensions. I won't try to graph them because, as we've seen, much more difficult to graph in 3 dimensions. Here we go. Sorry, I guess I get that a little straighter. There. All right. I've given you 2 points, A and B, and I'd first like to know what is the vector AB. Notice, by defining it this way, AB, I'm saying A is the initial point, B is the terminal point. So the vector AB, I take terminal minus initial. I'll write this one out. Terminal minus initial is going to be B minus A. So 5 minus 2. 2 minus negative 6. And negative 8 minus negative 3. Or 3, 4, negative 5. All right, I've also asked for the vector BA. This time B is my initial position. A is my terminal position. So to do the vector BA, I have to take A subtract B. So A subtract B, 2 minus 5, negative 6 minus 2, negative 3 minus negative 8. Gives me negative 3, negative 8, 5. I just realized I made an arithmetic mistake there, so we'll go back and fix it. All right, where I was going with this was I was going to say, now look, what happens when we have the same 2 points, A and B, but the vectors just switch their initial and terminal positions, when one vector is just the opposite of the other, and they would have been if I hadn't subtracted wrong. 2 minus a negative 6 is 8, not 4. Sorry about that. All right, and you can see that these vectors have the exact same values, just opposite signs. And that makes sense. They are simply the same 2 points, just in opposite directions. So if you looked at these on a graph, one vector would go that way, and then the other vector would go this way. All right, so that's part 1. We'll come back and finish this section in part 2.